Good afternoon, everyone, and welcome to today's Ethanol Producer Magazine webinar, Dryers Down to the Details, sponsored by Player Design, Inc. My name is Lisa Gibson. I'm the managing editor of Ethanol Producer Magazine, and I'll also be your moderator today. Before we get started, here's a quick word from our sponsor.
PDI is a manufacturer and supplier of rotary dryers and solid fuel energy systems. PDI drying systems are designed to meet the diverse needs of today's manufacturers. We provide innovative equipment that is cost-effective with environmentally compliant performance, responsive to even the most stringent guidelines. Our customized solutions use advanced technology to ensure a consistent quality finished product, giving our customers a competitive edge. PDI drying systems utilize precise airflow management and retention time controls, ensuring consistent outlet moisture. Our density classification means lower fuel consumption than traditional systems and reduces the emissions created by overdrying smaller materials. This leads to an overall system efficiency gain and limited operator interaction with the system. Efficiency of design allows a PDI system to generate higher throughput than conventional approaches in smaller drums. Our unique mechanical design on the outlet of the dryer lowers the horsepower required for the induced draft fan in a typical cyclone-based outlet. This approach reduces the need for secondary cyclones and allows for increased flexibility for material segregation. At PDI, our drying systems are engineered down to the last detail, from our T-section tracks and machined bearing mounts to our process design. Every item matters. PDI's experience in maintenance and operations is key to how we design our systems and ensures optimum performance for the long life you expect. At PDI, we are committed to unparalleled customer service and believe that our growth lies with the success of our customers. Visit our website at www.playerdesign.net or call 207-764-6811 for more information.
A big thank you to PDI for sponsoring today. A couple announcements I'd like to make before we get started. Today's webinar is being recorded. You'll be able to find that on the Ethanol Producer Magazine website. That's ethanolproducer.com. Check back in about a week. You'll be able to find this webinar on the webinars page underneath the events tab on that website. Again, that's ethanolproducer.com. We will have a Q&A session at the end of today's webinar after all of our speakers have delivered their presentations. Attendees will notice that you have a question box on your screen. You can type in and submit a question at any point during today's webinar. If you'd like to direct your question to a specific speaker, please indicate that. And in our Q&A session, I will go through and choose a few questions to go through with our speakers. Any questions that we don't get to will be forwarded to the appropriate speaker, along with the contact information of the person who has asked the question, so our panelists can continue to answer your inquiries even after we are out of time today. With all that out of the way, I think we're ready to get started. Dryers Down to the Details will feature 4 speakers. We have Tyler Player, who's the CEO of Player Design, Alan Nichols, Director of Research and Development for Raymond Elements, Inc., Josh Thompson, who's the Chief Technology Officer for Thompson Dryers, and Mick Henderson, who's the General Manager of Commonwealth Agri-Energy, LLC. We'll kick things off with Tyler. Go ahead, Tyler.
Okay, hi everyone. My name is Tyler Player, and I'm president of PDI. And currently, there it is. Okay, so on the agenda for today, I'm going to talk a little bit about flight designs, heating zones, different kinds of impact that these things have, how we introduce the product, how different folks introduce the product, and the advantages and disadvantages of different ones. Some pictures on dryer flighting design and some process results that we've seen across some other industries, across various industries, and then we'll open it up to questions at the very end. Lisa will open it up to that. one of the more common things that I hear about dryers is that basically they're all the same. When you're looking at a vessel that's like a 13 by 60 or similar size, that the performance will be the same no matter who makes it, and that's really not the case. Flighting design has a dramatic impact on how a dryer performs, including everything from energy usage, output quality, emissions, and many things in drying, like struggles with energy usage, moisture control, can be overcome with flight patterns of a different design. One of the things that we've done over time is try to utilize more and more and more of the drum. Our typical single pass drum has a lot of folks have very simple flight designs, and some have more complex. But as you look at them over time, you will see that making the material completely encompass the full width of the drum is incredibly important for correct drying gradient, and making sure that energy usage and moisture control are where you expect them to be. So as we've evolved over time, the newest flighting designs, this data represents what we've seen for temperatures throughout our drying process. We've tossed some little wireless thermocouples in there and tossed them around with the product, and the temperatures coming back kind of follow this pattern that you see here on this drum. And what we found was that once we got beyond about the first third of the drum, the heating dropped off dramatically with the proper flighting design. And what that allowed us to do was density classify the material. In other words, as the material dried, it could exit the dryer more quickly. And so the smaller, finer particles are able to float out of the drum after they get through the primary heating zone, whereas the wetter particles, the larger, heavier stuff, is able to stay in the drum for a significantly longer time, but reach its moisture content in a very gentle manner. And the other nice advantage of this is that energy consumption goes down dramatically, because you're not overheating particles that don't need it. There's no moisture evaporation in the particles that are, once they're dry, they have the ability to fluidize and float out of the dryer with a properly flighted drum. So these are just a couple of examples of some different flighting designs that we have. The ones on the left there are for a particular style of feed that we do. Those are density classification flights. That particular facility, those flights are intended for facilities that are mixing dry and wet material on the inlet, meaning they put material into the dryer that starts at 5 and ranges all the way up to 50% moisture, and have an expectation that when it comes out of the dryer, it's all plus or minus about 0.5% moisture content on the outlet. And they're allowed to mix any range of that. And the flighting design inside of there is what really makes that all possible. One of the larger things that we do from a mechanical point of view is the large internal clearances. It keeps material from hanging up and things from catching inside of the dryer. When they do that, they have a real much higher risk of fire. And the big thing that we gain from it overall is utilization of the drum from an energy point of view. It really helps with not over drying and not putting energy where it isn't needed. Trunnions and tracks. This is an advantage of properly flighted design. We spin our dryers, and a lot of single pass dryers spin this way, but they should spin 1 to 2 RPM if they are flighted properly. That spinning a dryer that slow makes a big difference in alignment issues, in seal issues, in all of the ongoing maintenance issues that you have with a typical dryer system. That people see. Rotating it much slower obviously makes the wear and tear significantly lower. So over time, you see a real benefit to it just in terms of how much you have to work on the machinery. This was one of the other changes that we've made over a series of iterations. A lot of dryers introduce product directly into the hot air duct coming into the dryer. And when you do that, you create a great deal of risk for fire on the inlet to the dryer, particularly when you're mixing drier materials on the inlet. What happens is those dry materials get dropped into a duct that might be, 850, 950 degrees. And with that sort of temperature comes a real risk that they dry out too fast and turn into a sparkler that floats on down the dryer and can cause a much more serious issue with the system. And this offset inlet allows the material to slide into the dryer without seeing that gas directly. That gas is introduced on the secondary side of it, and it has the ability to expand once it hits the dryer, and it also meets all of the wet product, and there's a significant steam cloud that develops right there in the first 5 feet or so of the drum that keeps that fire, drops that fire risk down significantly. And it's also been a huge advantage to us. I'll get to emissions in a few minutes, but that this sort of offset inlet has also dramatically impacted CO emissions and VOC emissions across a couple of industries, and those in turn impact the amount of treatment you have to do in the terms of VOC. So your energy efficiency goes up in the facility, and in terms of CO, that's mainly due to particles being ignited. At the inlet of the dryer, we discovered that they were with this offset inlet. That's no longer happening, and so the CO emissions were dropped dramatically. Recycle is a pretty common feature on dryers. It lowers fire risks. It improves emissions. It makes for stable gas conditions. Depending on the dryer system you have or don't have, recycle is something that's a long proven technology in the industry, and really can help stabilize things if you currently don't have it. If you do have it, controlling it can be a bit of a challenge, but once you get the balance right, it's definitely something that helps a lot with reducing exhaust to the stack and pollution control devices, which again goes back to overall energy consumption in a facility. So for a quick energy comparison, when I say standard dryer, that was our first generation dryer. Our newer one is the one on the right. Our first generation single pass dryer, if you look across, you'll see the incoming and outgoing temperatures are identical. But the sensible heat requirement of the previous dryer system was about 15% higher than the current one. And the reason is that the original flighting design allowed a lot of hot air to bypass the flow of material through the drum, and so we essentially had to increase outlet temperatures to get the material dry. And what we found with the latest generation of flighting designs is that we've cut energy consumption on the dryer by about 15%. And then, in addition to that, our original dryer used about 26 inches of water column to draw the material through. Our current setup takes about 16. And on a typical dryer of, a 12 by 50 or a 13 by 60 type dryer drum, you'd be looking at a brake horsepower requirement of 450 on the old one, and you need so you end up ultimately, because they don't make a 575 horsepower motor, you end up with a 600 horsepower motor, and your annual usage is significantly higher than, as you can see on the right. A density classifier uses only 16 inches of static, and the required motor drops way off to about a 350. So that 250 horsepower a year it's in the neighborhood of 40% in electricity savings on the fan alone. And it's been a significant advantage to a lot of the manufacturers we work with. The electric bill associated with that is significant. Just a quick touch for those out there that are interested in burners. We do make solid fuel burners. This particular picture is at a feed mill in Texas. It takes waste from the process and burns it in addition to natural gas. There's a natural gas supplemental burner with a solid fuel burner. You know, our systems can burn bark, we can burn dry fuel, we can burn, you know, we try to figure out a way to burn any basically carbon-based fuel, whether it's liquid or solid. So we do have quite a bit of burner technology if anybody's interested in that. So what I had done, just to give everybody a feel for the difference in the dryer designs, the newer dryer designs, this particular one is in the Carolinas, and it's mixed feedstock. The moisture content of the incoming material ranges from 50 to 50%. We replaced 3 dryers with a new energy system and single pass technology. They're finishing about 30,000 oven dry pounds per hour with no secondary VOC control and no formal PM control. And a lot of that goes to the flighting design, the outlet design that gets the lower 16 inches of static, makes a big difference in how much PM is created and how much has to be treated. The next case was, this one happens to be in the Northeast. It's mixed feedstock. Stuff comes in anywhere from 10 to 55% moisture. And when I say it comes in, that's basically what they drop on the inlet conveyor. And they're allowed to put all 55, all 10, or any combination therein, with any range therein. This replaced 2 dryers and energy systems, and it has a new bark burner. This one happens to be a wood products facility, but it's single pass process. They're finishing about 35,000 oven dry pounds per hour with no VOC control and no formal PM control. Again, very similar design to the other. And this was number 3. This one happens to be a feed plant. They actually bring in bakery feed, bakery waste, and make a feed product for feed mills out of it. The materials are anywhere from 5 to 60% moisture. They also dry a significant amount of solids from a local ethanol plant, before a local ethanol plant, and they mix that in as well. So this facility is running about 30 tons an hour of output of feed. They have no formal VOC or PM control on it, and this one is actually in New York State. And we have they are tested annually and have never had to have any sort of abatement system at all on the system. So on VOC emissions, this was the original design on the left-hand side. The red line represents what VOC emissions look like since the redesign with the flights and with the offset inlet. And we've seen VOCs drop off dramatically, as you can see there. Every one of these represents a set of 3 compliance tests at a facility that this technology is employed. And so that's dramatically what the impact on VOC is. Not necessarily to remove an RTO or some sort of secondary mechanism that treats VOC emissions, but it's a significant impact on gas emissions, or the gas consumption, natural gas consumption at the RTO. Then CO emissions were, as I mentioned earlier, with the offset inlet, it was an unexpected benefit. We were really trying to allow people to mix whatever they wanted on the inlet to the dryer and get a consistent moisture output. And what we found was the fire risk went down. We were seeing less sparks. We had improved stability in the furnace. We had improved drying control, and the CO emissions dropped by over 50%. Because what we discovered was we were, like I mentioned earlier, we were igniting the particles in the duct coming into the dryer, and the ignition of those particles was causing the CO. And with the newer design, you can see the CO drops off the radar of most permitted levels. And from a moisture control point of view, This was a particular facility that was targeting certain moisture. This time period elapsed here is about 24 hours. Those are the various samples and stuff. They had about 0.75% variation on the outlet moisture, and they were again mixing materials on the inlet that came in about anywhere from 5% moisture up to about 50. So they were, very wet material, very dry material mixed, dumped on the inlet of the dryer, and that's what flighting kind of does, and different flighting designs are out there for different manufacturers, but it makes a huge impact on the ability of the dryer to work properly and be stable. And then there's my contact information if anybody needs anything. Thank you, everyone, for listening and your time.
Thanks, Tyler. We had a lot of questions coming in during Tyler's presentation, so all attendees, please remember that you can type in your questions at any time during this webinar. They'll all come to me, and we'll have some questions at the end. Our next speaker is Alan Nichols. He's the Director of Research and Development for Raymond Elements, Inc. Take it away, Alan.
Yes, everyone. My name is Alan Nichols, and I am the Director of Research and Development for Raymond Elements. Raymond Elements is a fairly new company, formed in around 2007, and they have implemented a couple different new technologies, mostly geared towards the ethanol industry, but we also have some other applications for the compression dryer that we've been seeing interest in as well. One of the main things that Raymond Elements is known for is in 2011, we were able to produce the first 100% DDG range cube that had a very robust properties. During this development process, we noticed that we were getting a lot of moisture reduction when we configured the equipment in the right manner. And this is really what led to the design of the Raymond compression dryer. The two pieces of equipment, the bulk densification unit that produces the range cubes and the dryer, use similar technology, just in different configurations. So the Raymond compression dryer is very different in the industry than the ring dryers or the dryers that are being presented here. We operate our dryers on multiple engineering principles. The list here shows that there is a significant amount of shear, where we're actually rubbing the particles between the flights inside of the dryer. We work with principles of relative humidity, specific heat, rapid decompression. All of those lead to our ability to remove vapor from the product. You'll see in a little bit that the Raymond compression dryer runs at a much lower temperature. And by doing that, we have to use the dew points and relative humidities to express the fluid into vapor form and then extract it from the dryer. Versus vaporizing using heat of vaporization. The construction of the Raymond compression dryer uses custom hardware. The compression dryer is built very similar to a twin screw extruder, which mostly is in the plastic industry. Twin screw extruder will do your PVC piping, water lines, profiles, those kind of things. And so the compression dryer has adopted similar technology in the form factor of the machine, but has customized many design features to tailor it to work under the drying scenario. So kind of an explanation of how the system works. The Raymond dryer takes the product into the beginning section. The twin screw extrusion process is basically creates a positive displacement pump action of the material, and that forces it through the barrel to the outlet. During this process, there is a constant action of shear and pressure between the flights and between the root diameters of the screws. Once the RPMs get to a certain level, we generally run around 30 to 60. The higher the RPM, the more internal heat generation we get. Because of the shear and compression being directly acted upon the molecule of the grain, the heat gets absorbed directly into the material versus having to go through a convection process or even a conduction process. So then as it gets conditioned, we go into this cycle as shown. So the conditioning is the shearing and the compressing. Sometimes we view that as kind of like a kneading of dough type of process. And then the material gets warmed up. Specific zones in the barrel and the screws create a large amount of pressure. So we compress the material, we rapidly release it. At the same time, we're able to pull the exhaust from the machine. And in a little bit, you'll see the different zones and sections of how that's set up. So the screws are a big part of the design of the system. There are many different applications and many different functions that can be introduced into screw geometry to achieve many different operations. This is a CAD model of a current screw that we are using in our demo units that we have, where we can process specific grains and show outputs and rates and properties. In the lower left, you see the action of the screws. This extruder is counter-rotating. And so you'll see as those two, so the flights are opposite so that they mesh throughout the process. We can see a close-up view of where the action is happening on the grain. Shear mostly happens on the faces between the flights during the rotation, and then your compression is on the outer diameter of the flights and also the root diameter, as well as the sidewalls of the barrel. So there's multiple locations where we're able to get shear and compression. Looking at this more as the assembly level, you can see where the screws and the barrel coincide. We've laid out kind of the geometry changes and what is happening. You'll see again a conditioning zone and section when the grain first enters the system. It has to be brought to the proper temperature so that the properties can be affected well. Then you'll see compression and decompression zones. So at every compression and then right at the decompression zone, there's an exhaust vent where we're able to pull that vapor from the system. We generally pull that with about a -5 inches of vacuum. So some of the big benefits specifically for DDGs is color retention. We're able to process the grain without burning materials or adding color change due to those higher temperatures. We've seen where we can take wet cake, dry it to around 12% moisture, and virtually see no color change, even a possible lighting of the material. We have found that in the industry that's becoming more and more valuable and something that people are looking into to improve their secondary revenue streams. The other main thing that the Raymond compression dryer does to the grain is preserves that nutrients. There's a lot of plants that are now adding on high protein processes, high fiber processes, just trying to get that extra little bit of material as the feed starts to be used in different industries. Again, it's mainly to the low temperature. We run the material, but swings between about 205 and 180. The output can be right in that 150 range, and those can all be adjusted relatively easy. We know some of our customers outside of ethanol are looking for very specific temperature points where the degradation of those amino acids and properties happen at around the 155 level. So if we're able to keep that temperature 145, 150, and still accomplish the drying that are needed, then it yields for a much more desirable product. On the overall basis for the compression dryer, it's very appealing for capital investment with a lower price tag and infrastructure. We have had it tested on a couple instances where we've been able to show that the emissions are very low. Mainly that is due to the temperature that the material is seeing. The system can be configured in many different orientations and sections, and this allows us to pull material from the system at any moisture that someone would want to. So if we're taking it from 60 to 12 and somebody wants the modified 50, that can be pulled just right out at that stage. Or if they're looking for a 25 or something specific for a secondary process, that can be accommodated very easily. One of our other benefits is in the safety realm. Again, because of the low temperatures, we're able to run without much risk of fire or ignition. And really, we see this as not something that we have to deal with our system. The footprint of the system is simple and fairly small. That kind of goes to the infrastructure that is needed. We're able to install the system just on, a flat floor. All we need is some area, and things can happen very easily. And then we do have a scalability, which is nice. We can take and we've got 3 or 4 different size products to adjust throughput as well as moisture, and we can use a combination, or we can add additional lines without changing much infrastructure or conveyance schemes for that. So that's what I've prepared today, and we definitely have great information on our website, which is RaymondElements.com, that you can check out and get some more details if you wish. So thank you.
Thanks, Alan. Next up, we have Josh Thompson, who's the Chief Technology Officer of Thompson Dryers. Go ahead, Josh.
Good afternoon, everybody, and thank you, Alan, and thank you, Tyler, for your presentation. And Alan, I'd especially like to thank Raymond Industries for some delicious Oreo pellets that they give at VW. Anyways, my name is Josh Thompson. I'm a professional engineer, and I'm the Chief Technology of Thompson Dryers. I'm 4th generation owner of the company. It was originally started in 1945 by my grandfather, Ted Thompson. See if I can, I'm gonna get my screen to wiggle there. So there we go. So anyways, our first dryer back when we bought the system was a very simple dryer. It was just a dryer drum, a burner that actually burned right into the dryer chamber itself, the rotary drum. It was an outlet hopper and a cyclone, a few screws, and you might notice there are no fans in this. It was all natural draft. As all of you who run dryers might imagine, my grandfather became very frustrated with this immediately. And the first year, he tore out all the equipment and started building his own. This was also the beginning of our own technology that we've developed since 1945, as well as it was also a great way to keep our workers on during the off season. So Grandpa's mantra is equipment should work like it's supposed to, and that's ours to this day. So as time went on, 1947, we sold our first piece of equipment to another alfalfa dehydrating company, and then we opened our own manufacturing facility and started producing equipment. That facility has been closed, and we actually use manufacturing facilities all over the world now to produce our equipment as needed. Thompson has been in many different industries. We start off in alfalfa, of course, but we've gone into the forestry, the sugar industry, the brewing industry. We've done tests in the brewing industry, I should say, biomass, and in 1993 we entered into the, 1989 we started consulting in the ethanol industry and installed the first drying system of ours in the ethanol industry in 1993, a little plant called Alchem up in Grafton, North Dakota. At the time it was a whopper at 10 million gallons. This plant here is a 30 million gallon plant, and it is been in operation since 1994 and still running, and still original dryers in it. So what is drying? I'm going to start here. We've all talked about this so far, and when we get to water removal, I think we'll just let what Raymond Industries said stand. But evaporation really is a state change in water. Go from liquid water to steam. And we do this in our dryers by raising the heat, and we use natural gas typically to do that in the ethanol industry. There are some other plants that do some different things, but I would say 90% or higher than 90% use natural gas. And you might wonder how much water energy it takes to evaporate water. Well, if in the typical ethanol plant, you're going to be right around 1,025 BTUs per pound of water evaporated. And you'll see later on the presentation that it's going to take every dryer more to do that. It just, the way physics works. And the distinction to be made is here between us and water removal, that you can remove a lot of water at a lot less energy because you're not evaporating it. That state change does take a lot. And we certainly do employ some use of water removal with centrifuges and the like and evaporators. So we offer a rotary dryer, very similar to many. As I said, we develop our own technology. So a lot of this schematically looks the same, but there is some process stuff that's different. First off is our heat source, which is the combustion chamber, the burner, and the combustion air fan. The combustion chamber does a couple different things. It allows a chance for the flame to fully develop inside of it, and we introduce our recycled gases around the flame in such a way that we do not impinge the flame and leave the flame completely free to develop without the introduction of recycled gases. But along with that, we're able to cool the flame as it's developing to keep the NOx formation down. Without impinging the flame too, we do reduce any kind of carbon monoxide, and we also reduce the any VOC generation that would be from incorrect combustion. Oops. Next is our dryer drum. Our dryer drum is built very stout to count for many years of operation. We have had drums in service now that have been in service over 50 years. I actually ran into one in a little molasses plant that I was like, that looks like our drum, and did some research, and sure enough it was. It had been moved all about the country from here to there. And that was a 1960s model drum and still in operation. And that was back in the late 2000s, 2009, 2007, somewhere in there. So, so I guess that was slightly less than 50 years. Sorry about that. Anyways, our dryer drum is designed to do a couple things. Actually, the flighting inside of it is to put the product in contact with the hot drying gases produced from the combustion chamber. And as my dad likes to say, as long as you can get the product where it's supposed to be, Mother Nature pretty much takes care of the rest, and proper flighting design allows for that. It's very important, as was mentioned earlier, to make sure that the product is in the right place at the right time with the gas flow. And by doing that, we're able to have low emissions and a proper drying all the way through the drum. The next section is our product removal. Thompson employs two different methods of product removal, which helps with the emissions as well. Our first is a outlet hopper, which is going to take care of about 90%-ish of the material that comes out of the drum. And the remaining product goes to the cyclones. And truthfully, this makes the cyclones a little quote-unquote less efficient, but when you get, let's say, 90% less than what you're used to getting, it doesn't take much efficiency to really have a good overall product removal efficiency for the system. We use 6 cyclones that are small in this particular configuration. This is for a 50 million gallon drum that we designed, and is actually in operation. Each cyclone has an airlock, and the point is, with 6 cyclones, we're able to get really good product removal efficiency with very low pressure drop. The next is, of course, the exhaust and final cleanup. In the ethanol industry, we are required to have RTOs, or thermal oxidation in either an RTO or some sort of thermal oxidizer, like a Hersig is very popular too. This shows just the dump stack, which is needed to make sure that we all have that for safety to meet the NFPA requirements and not purging through a thermal oxidizer if needed, and also to allow in case of an upset condition, allow things to go to atmosphere so we can shut down the system properly. And of course, there's an oxidizer to take care of the rest of the emissions that is required. So part of the Thompson difference is we make a heavy industrial piece of equipment. I know everybody does, and I will give you our definition of what that means. During normal operation, there are no stresses in the fabricated parts that are known to exceed the cyclic endurance limits or static yield strength of materials of fabrication. This means basically, as you probably all know, that you can apply a lot of force to a piece of metal and not break it, but you can put a lot of force on a piece of metal a whole bunch of times and break it eventually. And what we've done is we've designed our drums especially to not have any kind of movement as they roll. If any kind of rolling drum, I don't care how stiff or robust it is going to roll in essence like if you very exaggerated example, is like a rolling water balloon. And if you can keep that drum from looking too much like the whirling water balloon, you really increase its lifespan. I've been in drums and measured them myself that have been up to 25 thousandths wider than they are tall at any given time. And we try to keep ours well into the 30 thousandths to 60 thousandths wider than taller at any given time. And with that, the stresses we put on the drum, we can expect a 30+ year longevity, including stainless steel dryers. And stainless steel is something to be careful of. With flexing, stainless steel work hardens and will crack, and there is a possibility, if the drum is not designed right, that it can end up on the floor. So the other, too many clicks there. Some other stuff about Thompson difference is we have a low electricity usage. For our entire dryer system, including the conveying, mixing, and the like, across the line for a 50 million gallon plant, we're going to have slightly under 800 horsepower, and then we'll use less than 600 horsepower. And about 250 of that to 300 is the fans on that. Again, on a 70 million gallon plant, we have about 950 horsepower across the line. That's the motor sizes, and we use about 650 horsepower. And then back to our natural gas. As told you earlier, it takes 1025 BTUs per pound of water evaporated, and Thompson does ours for slightly less than 1300 BTUs per pound evaporated. We do this by, again, that robustness in our drying. Part of the benefit of that is we're able to keep that the drum very, very round as part of our structure, which means that we can keep our our track's round, which the rolls on the trunnions, or the tires that most people called it. And if our tires are round, our drum is round, we can actually make our seals very round. And with round seals, sealing the drum up becomes very, very easy. We can use a very simple sealing solution, which is really just a heavy-duty, high-temperature rubber belting that's pulled to the appropriate tightness. For a 50 million gallon plant, we're looking at about 73 million BTUs an hour, give or take, depending on the process. And for a 70 million gallon per year plant, we're looking at about 92 million BTUs per hour, give or take, based on the process itself. One of the other benefits of a Thompson dryer is a gentle drying, and we do this with basically the use of our recycle. But the recycle allows us to have a low inlet temperature and fairly moderate outlet temperature. We typically design somewhere between the 255 and 235 mark outlet temperature. The recycle allows us to do this, and the exhaust gas recycle has been mentioned. Most dryers use it. And we certainly do, and we started using it back in the 60s. And what we found out was the use of this is extremely important to be steady and stable. And we control that ourselves. That's actually part of the control loop. And what recycle does is it allows for a very moist drying media. So the steam in the drying media, steam has got a specific heat that allows us to transfer more energy into the product at a lower temperature. And much like not wanting to get a steam burn because it cooks right through you, steam also heats up right through the particle. So you're able to heat the particle from the middle out, which really promotes good drying. And by good drying, we can do drying with the least amount of energy as possible, as well as create do less thermal damage to the product, which causes VOCs and other basically particulate emissions. Part of our control system is stable operations. This is proprietary, but we do control 3 different parts of the system as far as we control our exhaust gas recycle loop. We control the pressure inside the drum to maintain so we meter out what we need to account for the gases of evaporation as well as the combustion. And we also control our outlet temperature. This has given us a very steady operation throughout the years and is continuing to do us a lot of good. We don't use any dampers in our system as far as we can avoid it. Dampers are just a pain in general. The controllability, the increased pressure drop, and maintenance headaches of them all. It's been said many times that I can spend $10,000 getting some dampers to work right, and man, they'll work great for about a year, and then they get to the point they just fail because of all the extreme conditions of operation. So we got tired of that and used VFDs, and that has worked out very, very well for us. It also cuts down a lot of horsepower and has generally made the operation of the system very consistent. We don't use any refractory in our system if we can avoid it. A complete refractory combustion chamber usually has about, as a rule of thumb, the amount of BTUs you're using per hour stored in it. So if I'm 50 million gallon plant at 72 million BTUs an hour, I have about 72 million BTUs stored in my combustion chamber refractory. And in case of some sort of mishap with the system, or if it lose a feed of some sort, what that does, I got to get rid of that heat, and I have dry feed in the system, and it really does cause a danger regarding fires and explosions. So we've taken that out. It also allows for faster startups and very quick shutdowns as far as getting the heat out. So if something goes wrong, you can get in and fix it quickly. So here's a schematic of our dryer system that's typical. This is for a you see a 50 million gallon plant. Here is basically it's similar to most people. We got the combustion chamber, and I might add that the reason a combustion chamber is such that it is, we've gotten away from using combustion chambers that are put directly into the drum like was shown in our first slide, simply because that really does causes a lot of damage to the product. Just the brightness of the flame, the radiation from the flame itself is bad on things. And so we make it turn a couple corners, which helps our mixing and gives us a really nice non-stratified gas going into the drum, as well as yeah, anyways, got ahead of myself. So product goes into drum. We talked about the drum and the outlet hopper. Notice that again, that the cyclones, we do use airlocks under each cyclone, so we don't have flow going from one cyclone to the other and causing an emissions problem. I think the big thing that you'll notice here that's different than most other rotary dryer systems is the two different fans, the FGR fan, the exhaust gas recycle, or flue gas recycle, and the vent fan. Of course, there's dampers on the dump stack. We obviously have to have that for our going to the RTO. So that is just about concluding my talk here. Here is a table showing basically the sizes of dryers we'd use and some typical DDGS output and energy requirements for those. Our largest drum per yet in the ethanol industry is a 16-foot, and we should be starting up early next year. And we have the 50 million gallon that's been running for several years, and several 12-foots all around the industry. So again, if you have any questions, please ask, and we'll answer them all soon. Thank you very much.
Thanks, Josh. Next, we have Mick Henderson, who's the General Manager of Commonwealth Agri-Energy, LLC. Go ahead, Mick.
Hey, Lisa. Well, those are some good presentations. I'm excited to be part of this as a user, not a seller of equipment or design entrepreneur, but as a business that's looking at operating plants, an ethanol plant with a drying capacity for present rate and future expansion, and trying to do energy efficiencies. Our business in I had to click first. Okay. Our business in Hopkinsville, Kentucky, is adjacent to the Hopkinsville Elevator Company grain elevator, and you can see we're a member of a family of companies of a 3,400 member, 100% farmer-owned co-op. And that's a picture of our location. One of these drones, you can get do some pretty neat photography over your plants these days. All of our profits roll up to our parent company and distributed annually, 40% in the year we make it, and 60% after a 5-year retainage. And keep that in mind when you try to sell us equipment. A 5-year return on investment keeps my farmers happy. This last fiscal year, we produced 35.1 million fuel ethanol gallons and utilized 11.9 million bushels of corn. We produced 100,000 tons of DDGs, 75,000 tons of CO2, and 5,000 tons of corn distillers oil. We've improved our efficiencies this last year to achieve our highest ethanol yield ever at 2.95 gallons per bushel, with a lower natural gas usage per gallon, also better than ever before. We received a new Kentucky air permit to expand production last December. We received that same month an efficient ethanol producer pathway permit with the federal EPA. This federal permit requires us to achieve ethanol yield from corn, natural gas usage per gallon, and electricity usage per gallon as an improvement to our carbon footprint as it compares to gasoline. We intend to operate, and have been for this last year, at this level, at an improved level, at a permit allowed level, and expand our business to 45 million gallons per year and 15 million bushels of corn per year by May 2018. Our distillers' grains have continued strong values to corn and soybean meal as a component livestock feed, We mostly ship by truck. We do ship some by barge from our Clarksville port, 25 miles to the south. Wet feeds are sold locally to beef and dairy farmers, but predominantly 95% of our distillers' dried grains is sold to poultry. Poultry is the #1 commodity in the state of Kentucky. Distillers' corn oil is also mostly sold to local poultry as an animal feed fat, and it is sold as a biodiesel feedstock. That expansion I mentioned, $17.4 million in capital improvements, $7.2 million is planned for efficiency improvements. Make sure I can make that producer pathway permit, as well as $10.2 million planned for increased capacity. Again, all expected to be done by May of 2018. So how our plant operates. We're similar to most ethanol plants in the U.S. All these ideas of the previous speakers are interesting and pertinent. We're right now operating at about a 40 million gallon per year dry grind rate. I updated from what I put on the slide here because really that's just in the last couple of months we've done this. We operate with whole stillage centrifuges. We target 80% torque and 67% solids. But as that one slide of the previous speaker showed water removal versus water evaporation, we do a lot better job with a lot lower natural gas use if we spin the water out in the centrifuge before it ever gets to the dryer. That gives us about 25 to 30% backset, and whatever we don't use in backset in the recirc, we run through evaporators that drive distillation and make 35 to 40% solid syrup, which again is another place we could address water removal by some of the latest technologies, or use some old technologies in a new plant to take those solids of the syrup on up, because ultimately our syrup goes back on our feed. Better to evaporate it out with an evaporator than put it through a dryer. Our corn distiller's oil with a flat wig tricanner does remove the animal feed fat, does reduce the heat load on the dryer some, and we're about 0.8 pounds per bushel right now. Okay, so that leads us to the dryers. There are two ICM gas-fired rotary drum dryers. We're drying 110,000 tons per year of DDGs. Our emissions are controlled with ICM thermal oxidizer and Herzig to make our steam for the plant, as well as an Eisenman RTO. We did do an upgrade a 3 years ago with a Honeywell Slate upgrade on the thermal oxidizer to improve the combustion control of the gas train. Basically, they bought out Maxon valves, and we've utilized them to improve our efficiencies in our combustion control, and expect to do so with the dryers. Maybe with one of these companies that just presented previous, or similar, because the gas control is still an issue with the present dryers. Those two gas-fired dryers today target inlet temperatures about 600 degrees, outlet temperature, the first dryer in a 2-dryer set in series, 600 degrees on the first dryer, 180 degrees on its outlet, 500 degrees on the second inlet temp with a 220 degree control outlet temp. We do that with 100% recycled gas. I got a 200 horsepower ID fan on each dryer, and we run that recycled damper 100% open, and pretty much want to take the damper control out of there, keep it wide open. The recycle feed comes back to the cake and syrup and a mixer preceding the dryer, and does a real good job of getting us down around 50% moisture on the inlet of the dryer, so it's not just a real sloppy cake to go in that inlet. You need that to be flowable as it first hits the lifting paddles. The finished DDG dryer moisture targets 11 to 12%. I guess I should advance the slide so you can see what I'm talking about. I did write some of this down. I guess it was on that other. It's still on there. Okay, finished DDG dryer moisture 11 to 12%. That's done today, and we probably controlled it manually for a decade, and we finally learned a valuable lesson of the original design and control that pressure, control that outlet pressure, and then control the back end temperature by throttling the gas valve and the linkage to control the combustion air fan. Control the temperature. Don't just let it run wild and try to feed it constant. You can actually control that temperature and get that target within that control range. Do that a little bit with an incentive by saying every employee in the plant, as part of their monthly performance incentive, can get a $100 bonus if all the daily retains are within 10.5 to 12% moisture. It works sometimes. It's a component of an $800 per month potential bonus, and they got $600 of it last month, but they missed that $100 because they had like 12 days they were out of spec on that moisture. But it can be done. We do it, and it has to have an operator input. You have to keep your centrifuges consistent, which is something last week when you try to keep your centrifuges running when they really need to go out for a rebuild, and you keep running them, and they go out on torque, they go out, make slop, so you vary your feed to the dryer. Guess what happens with your moisture on the back end or control your dryer? And ultimately, you have to keep the dryer lit. We had one last night that tripped out 7 times. And it might be a fire eye. We're still troubleshooting it today, but you can't be efficient and you can't maintain good quality if you don't keep your equipment maintained. And that's not just the dryer itself. That's upstream all the way back to fermentation. If you don't have good fermentation, don't have consistent feed, you won't get there. Okay, so what we're looking for. Increasing our capacity to 45 million gallons per year with improved efficiency. I have to be improved efficiency first, or I can't make gallons above my my permit limit. My permit limit was 35 million gallons. We got that approved to go on up. But the 2007 definition of a grandfathered plant, I have to be efficient producer pathway efficient to make any more gallons than that. So we have to front load our projects by being more energy efficient. I kind of explained that efficient producer pathway requirements. So what are cost-effective solutions? The capital cost balanced with operator cost for best value. Well, we have 2 dryers that probably can do 100% of our drying for the expansion. I say probably. We might have our burner temperatures 700, 800 degrees. Or we might have more equipment failures. I got to run the centrifuges right. There are solutions, but I got to balance out the capital costs versus operating costs. That also goes with ingredient costs. There's some things upstream you can do that improve that. And ultimately, the next projects we might do beyond our expansion of May 2018 are differentiating feed products. Talking to some vendors just in the last few days, high protein feed for poultry. I'm in a poultry region. I might want to differentiate my feeds and do a stream of high protein feed. And then what do I do with the fiber? What is the value of the fiber I have left? And ultimately, the partners that will work with us in the long term. Excuse me. So what we're trying to do is run our business best we can. We're not the worst out there. I wanted to just throw this out there and brag about my crew a little bit. This year we were recognized by the Kentucky Association of Manufacturers as Manufacturer of the Year. That's for businesses under 100 employees, but we look forward to another great year at our ethanol plant and to run it well. That's all I got, Lisa.
Okay, thank you, Mick, and thank you to all of our panelists. We do have quite a few questions, so I'm going to go ahead and get started. Our first one is for Tyler at Player Design. Can biogas be used at 100%? How clean does it have to be?
the short answer is at 100%, it would have to be pretty clean. I've never used it at 100%. We've used it north of 90, but never at 100. I'd defer to other panelists if they've ever used it at 100.
Would anyone else like to weigh in on that? Thank you, Tyler.
Yeah,
Okay,
this is
we'll move on.
Josh. Yeah. Oh, yeah, this is Josh Thompson. Sorry, it took me a while to get the off mute.
No problem.
Yeah. Yeah, I would agree very much with Tyler on that. It really depends on the biogas, excuse me, of how much you can use.
Okay, thanks, Josh. Our next question is for Alan about Raymond Elements. What is the normal capacity in tons per hour, and what is the maximum capacity?
Yes. So we do have, like I was mentioning, a very scalable system. Currently, we are installing a system that's going to run 90 tons per day of dry 12% grain. And we've also designed systems that can go up to 200 tons a day and even beyond. With the way our system works, it's almost direct scalability for size of barrel, size of screw, and throughput.
Okay, thanks, Alan. Next, we have a question for Mick of Commonwealth Agri-Energy. Any new upcoming projects?
What's that for Raymond?
Well, yeah.
Or
for Commonwealth.
Okay.
And maybe with Raymond. Maybe that's what he's trying to tell you. As we have, in fact, we went to visit their site to see their operation. It's a neat process. That's what we're evaluating. What will we do next? And that the comments I kind of had, that's why I got a tickle in my throat and I couldn't talk very well there for a bit. But the projects are best ROI. You know, we might say that when we push our dryers to the 50 million gallon capacity for R2, and that's probably about a functional limit when you say 800, 900 degree Fahrenheit on the front end of the dryer, what do you do next? Those projects should include how do you fine tune and get more out of the dryers you have. That may be the lowest cost thing to do, or an incremental capacity, and that's where Raymond might be able to do an incremental piece, or any of the speakers' businesses could give you an improvement of what you have. That's not just a whole new dryer. But you might also differentiate in different products. There you might need 2 separate dryers for 2 separate products. That's just the tip of an iceberg. Sky's the limit.
And this is Alan. I was going to comment on what Mick was saying. Sure. Yes, we've definitely been working with different plants to where we can increase throughput of the existing systems that they have. Mainly looking at just where each piece of equipment hits its sweet spot for efficiency. We've been looking at taking in some of the higher moistures because our system can start the process in the 70s. We can do it with syrups. We can do it with some of that. And we can put just a single stage to exit into their dryer right where the dryer wants it. So we've seen that as just an add-on for increased production.
Thanks, Alan. Our next question is for Josh Thompson with Thompson Dryers. What is the expected percentage of DDGs being recycled and burned in the combustion chamber?
That is hard to answer. It is very low. There is, the percentage of DDG that would be burned in the combustion chamber, I would say is less than 1 to 2%. I think that's the easy answer, but it is really hard to know how much is actually going on with that.
Okay, Thanks, Josh.
Yeah, and that would be, I just want to say that would be in our dryers. I've seen other dryers where they are actually getting several million BTUs an hour out of that same problem. So basically, they're burning their feed as a fuel in their dryer. So it's
okay. Our next question is for Tyler with PDI. What is the typical service life and efficiency of the dryer seals?
So typical seals for us, it somewhat depends, but a typical seal for us is the most recent generation has been in 3 years and 4 or 5 locations and still there, so kind of in that neighborhood. You know, it's not something we spend an inordinate amount of time on seals anymore. We worked out a design that works. I hope that answers the question.
Okay, thank you. Our next question is not directed toward anyone specifically, so I think we'll just go down the line and let everyone answer. The question is, does anyone use a natural gas-driven engine to drive the fans and then recover the heat from the engine? Tyler, do you have anything you'd like to say in response to that question?
The short answer is I've seen several people try it. I have never seen anybody scale it to a production volume that where they used it, but that's my experience.
Okay, how about Alan? Again, the question is, does anyone use a natural gas-driven engine to drive the fans and then recover the heat from the engine?
So that question really applies to the different style of drying method. So no, I don't have really anything to comment on that.
Sure. Okay. Josh or Mick?
This is Josh, and I have not seen that, and I have not done that.
Okay. Our next question is for Tyler at PDI. I am carrying out waste heat recovery prior to drying. Can you accept inlet gas temps as low as 250 Fahrenheit or 400 Fahrenheit?
400 is easy to do. 250 takes a really big dryer to do effectively. But 400 works. 400 works, and typically, if you were down at 250, you'd want to. It's pretty hard to get a lot of drying value out of that, but you can do 400 pretty easily. We have a lot of dryers that run in that temperature range.
Okay, thank you. Another question for you, Tyler. Do you offer services for finding root cause and fixing cracks on existing dryers of other manufacturers?
That's a complicated question. We would certainly give anybody a hand that was looking for it. And so the short answer is yes, we could come out and look at it.
Okay, thank you. Next, we have a question for Raymond Elements. So this one is for Alan. On the conditioning screw side, where do you have to get the product to the correct temperature? Do you ever have to add steam there? So again, on the conditioning screw side, where you have to get the product to the correct temperature, do you ever have to add steam there?
So right now our system works, it's a full electric for the energy usage. So we don't add any peripheral steam. During the conditioning section, we like to get the DDG on a standard product up to about 205.
Okay, and then another one here for you, Alan. Have you designed modular dryers that are containerized and roadworthy?
We haven't specifically designed for that purpose, but we do have one. It's actually our trade show unit that was there at the show, and we have sent that to 2 different facilities, and they're able to set it up there to run whatever specific products they have. because our lab is in Colorado where we can do a lot of work, but shipping wet distillers, you can't check nutrients after because it'll spoil so quickly. So we do have that option. It's not like a self-contained traveling unit, but it can be moved fairly easily from plant to plant.
Okay, thank you. We will go through one last question. This one is for Thompson, so this one will be for Josh. Does the refractory help with complete combustion of the fuel and any CO created or any VOCs recirculated back to the furnace?
It can, but if I find with a properly designed combustion chamber that's large enough, we actually design our combustion chambers oversized so they have the proper room for combustion. So yes, that can happen, but with a good combustion chamber, you do not need to do that.
Okay, a big thank you to all of our panelists today, as well as Player Design for sponsoring. If you want to learn more about PDI, you can visit playerdesign.net. We also have an exclusive discount off of the early bird rate for all attendees of today's webinar for the International Fuel Ethanol Workshop and Expo that's coming up in June from the 11th to the 13th in Omaha, Nebraska. You can call the number on your screen, mention FEW webinar to take advantage of that discount, and that expires on March 6th. So make sure you do that before then. We also have a few events coming up. December 20th, the Biodiesel Magazine webinar series is presenting Keeping the Flow, a crash course on biodiesel cold flow improvers. The International Biomass Conference and Expo and the Biomass Carbonization and Torrefaction Summit are both coming up in April in Atlanta. And of course, the International Fuel Ethanol Workshop and Expo, as well as its co-located Advanced Biofuels Conference, coming up June 11th through the 13th in Omaha. Thank you everyone for attending today. Enjoy the rest of your day.